Here's another example where we're going to graph a polynomial function using end behavior and intercepts. So first, determining end behavior for a polynomial depends on its degree and its leading coefficient. So before we decide the end behavior for this particular polynomial, we're going to need to determine its degree and its leading coefficient. Degree is one of the few things that's harder to find when the polynomial is in factored form. So it's the highest power of x overall in this expression. So imagine that you multiply this out. You'd have negative 1/3, so that's just a constant, times x squared, and then some other stuff. Actually, if you square x minus 1, you get x squared minus 2x plus 1, if you remember that. But the important thing is that you're going to have negative 1/3 times x squared, and then some other stuff, times x squared minus 9. So when you multiply that out, your leading term is going to be negative 1/3 times x squared is x to the 4th, and then some other stuff. But with end behavior, we're focused only on the leading term, the negative 1/3 x to the 4th. We don't even need to bother figuring out what all that other stuff is that comes after it. Looking at that leading term, we know that the degree is 4, which the thing to note about the degree is the fact that it's even, and the leading coefficient is negative 1/3. So the thing to note about that is that it's got a negative leading coefficient. When your polynomial has even degree, picture y equals x squared. So the parabola. When you have a positive squared term, your parabola opens upward. When you have a negative in front of your x squared, it opens downward. That extends to, for at least as far as end behavior goes, to just any polynomial with even degree. When it's got even degree, either both ends point up or both ends point down, depending on your leading coefficient. When the leading coefficient is negative like this, then just like with parabolas, when you have a negative leading coefficient, both ends of the graph are going to point down. So I'm going to erase this. We don't really need that anymore. Once we have the degree and the leading coefficient, then we know that the end behavior is going to be down on the left, down on the right. It points down on both ends. Okay, intercepts. X-intercepts are the zeros of the polynomial. To find the x-intercepts, we need to take that function, in this case negative 1/3 x minus 1 squared, x squared minus 9, and set that equal to 0. Now, notice that this is not completely factored. This x squared minus 9 can be factored a little further, and I think that's what I want to do next, is to take that x squared minus 9 and break it down further. That's a difference of squares. This can be factored as x minus 3 times x plus 3. And so I have negative 1/3 x minus 1 squared times x minus 3 times x plus 3 equals 0. So the zeros of this polynomial are x equals 1, x equals 3, x equals negative 3. We should also note the multiplicity of each of these zeros. So the fact that you have x minus 1 squared means that 1 is a zero of multiplicity 2. We have x minus 3 to the first, so 3 is a zero of multiplicity 1. And also negative 3 came from this factor, which is to the first power, so that's also a zero of multiplicity 1. Remember that whenever the multiplicity is odd, like it is in each of these cases, the graph will go through the x-axis. So at each of these values, 3 and negative 3, the graph will go through the x-axis. When your multiplicity is even, the graph will touch the x-axis and turn around. I'm just going to put touches and turns because of the space that I have here. So at 1, the graph will touch the x-axis and turn around because of its even multiplicity. At 3 and negative 3, the graph will go through the x-axis because of their odd multiplicity. last thing, and Y-intercept honestly is kind of optional, but we could find the Y-intercept by plugging 0 into this function. So the Y-intercept is f of 0, which will be negative 1/3 times 0 minus 1, so that's negative 1 squared, times 0 squared minus 9, so that's negative 9. I'm getting this right here by plugging 0 into this function. Negative 1/3 times negative 1 squared times negative 9 to the first. And so this will be negative 1/3 times positive 1, so that's negative 1/3 still, times negative 9 will give me positive 3. I'm sorry, it's way down here in the bottom of the board. But now we can collect that information and draw an overall sketch of the graph. So now when you're ready to graph these polynomials, start by plotting the x-intercepts. So this one has x-intercepts at 1, 3, and negative 3. X-intercepts at 1, 3, and negative 3. Second, use end behavior to draw the ends of that graph. So end behavior is down on the left, so go to the far left x-intercept, draw the graph going down from there. And down on the right, so go to the far right x-intercept, draw the graph going down from there. And then use multiplicities to fill in the middle. So what I mean by using multiplicity to fill in the middle section of the graph is use this, what we talked about here. So at negative 3, this was odd multiplicity, the graph goes through the x-axis. Now here's where we could actually use, so the y-intercept was at 3, we can make sure that we plot that y-intercept at positive 3. And so your graph is going to go up, it goes through the x-axis, maybe it even goes higher, we don't really know. At some point it turns around, it's going to go through that y-intercept at 3 and come down to this next x-intercept, which is at 1. Now at 1, this has even multiplicity, so the graph will touch the x-axis and turn around. Touch the x-axis and turn around. And then at some point come and touch this next x-intercept at positive 3. Positive 3 has multiplicity 1. It has odd multiplicity, so the graph goes through the x-axis. And so here's a rough sketch of the graph of this polynomial.